Hi there, and welcome to the 7th lecture in our quantum field theory course. Today, in this lecture, we're going to think about interactions, or rather, we're going to start to work towards the formalism required to describe interactions, so interacting field theories. There's quite a bit of extra machinery we have to add on top of the stuff we've already developed for free field theories. So in today's lecture, we're going to start with that, and then the next lecture we'll sort of continue developing all of that technology and extra conceptual stuff that we need. Okay, so just as a motivation, let me remind you again of the problem. Maybe not problem, the limitation is maybe a better word, of field theories that are free. That is to say, field theories that are like the theory that we've considered so far, which just has this kinetic term, this d mu phi, and a mass term. So we can consider an operator, let me call it n, small n, which is defined to be d3p over 2 pi cubed ap dagger ap. So this is a special operator. This is called the number operator. So this just counts the number of particles in a state. Okay, so with some of the states we have already considered, for instance, the state just labeled by p, so we know this is describing a single particle with momentum p. This number operator returns the number 1, because there's one particle. And if we act with the state with 2 particles, so we also constructed this state, p1, p2, which has 2 particles, one with momentum 1, one with momentum 2. This would return the number 2, because there's 2 particles in the state. Okay, so we can see how this number operator evolves with time by using the Heisenberg equation of motion. So if we use the Heisenberg equation of motion on this operator, which is I, this operator we want with the Hamiltonian, we find that, well, this Hamiltonian operator can actually be expressed as omega p times the number operator. Okay, so the only difference between the number operator and the Hamiltonian operator, we had an omega p factor, okay, but the omega p would fit in there. So in other words, I guess I should be a little bit careful because I don't want to pull it outside of the integral. This is what we would have. But whenever we look at the commutator, since this Hamiltonian operator is essentially the same as the number operator, but with this extra omega p factor, this commutator is going to vanish. It's going to be 0. So in other words, the ndt, the evolution of this thing with time, is 0. So that tells us that in these free theories, the number of particles can't change. Okay, it's a constant, so it can't change. It has to be the same for all time. But of course, in the real world, we know we do have theories where the number of particles can change. For instance, I bring an electron and a positron together. They annihilate, they have disappeared, and they could go into 2 photons or something else. So clearly, in the types of theories we want to describe in the real world, we do want numbers of particles to change. Another example would be the Higgs. So the Higgs is a scalar particle, so maybe that's a better choice. If I take the Higgs, I know that it can change into 2 photons through a decay mechanism. But in the formalism we have so far, that's not possible. So this is why we have to go beyond what we have done before. So what we want to go on and do then is to describe theories where we have interactions in them. And in particular, as particle physicists, often we find information about particles through scattering processes, be that at colliders where you slam particles together, or dark matter detectors where you try and look for the scattering process where a dark matter particle comes through and interacts in the detector, or neutrino detectors or whatever. But quite often we're dealing with scattering processes. And so one of the things we need to be able to describe in scattering processes is the evolution of a particle from one space-time point to another, right? So from one end of a collider to another, or one end of the galaxy to my dark matter detector in the Earth's frame. So the formalism we need to describe this change going from one space-time point to another, we need to investigate what are called propagators. Okay, so let's define and look at the properties of these propagator objects. So just to remind you, in the last lecture, we very briefly discussed different states. So we discussed in particular that you could construct one particle position eigenstates. So we said that you can construct these by acting with the field operator, and here it's the Schrödinger field operator, so there's no time dependence. If we have the Schrödinger operator acting on the vacuum state, we produce a particle which is at a definite position. Okay. Now we can generalize it's actually right generalization to the case when we have not just position but time in the game. So now we want to consider something which is at some space-time point at a time t. Okay, so quite often we'll just write this as x. Okay, so when we put the underline or the line under the object, we're thinking about the vector, and when there's no line, we're not thinking about the 4 vector. So this x is simply the Heisenberg field operator. The Heisenberg field operator is a function of position x and time t. And again, quite often we simply wrote this as x, 0. So there's no underline over the x, unlike in the case with the Schrödinger operators where we were indicating it was a vector. Okay, so next we want to think about, a particle going from one space-time point to another. So the way we describe this in quantum mechanics is using amplitudes, because obviously these are quantum mechanical objects, so they don't follow definite trajectories, but we can work out what the amplitude is, that if we have a particle which starts at one point, that we'll find it at another point. Okay, so let's think about the amplitude for a particle to propagate. So this is where the propagator comes from, propagator term comes from. Let's think about propagating from a space-time point y. So this means it has a time component y0, a spatial component, the vector y. We'll go from y to x. Okay, so x again has a time component and has a spatial component. So this we can write as, we want to start in y, have a ket y, and we want to find the amplitude that it ends up at x. So this, using our definition above, okay, this is simply going to be 0, x, y, 0. So this is just the propagator. So let's introduce some notation that you'll often see in field theory books. We're going to follow. So the notation for this combination of fields sandwiched between a vacuum state is quite often written as D. I don't quite know where D comes from, but it's given the notation D. So this is exactly what we have above. Okay, and just as an aside, so this is a notation that's usually in the books where you have the minus sign. It can also be useful to think of this as y going to x. Okay, so when we write it as x minus y in this way, this is this very particular combination. And it's the combination where y is on the right hand side, so it's going from y to x. So books don't tend to use this notation with an arrow, but it can sometimes be useful to think of it in that way, so you remember the direction of the propagation. Now it's straightforward to evaluate what this propagator is, and we can do it because we know, or we have expressions for the field in terms of these raising and lowering operators. Okay, so just to remind you, I've written it a lot of times now, so hopefully you're familiar with this, but it's the integral of d 3p 2 pi cubed 1 over root 2 omega p, and then we have the combination of the lowering operators and the creation and annihilation operators. So when we want to evaluate d of x minus y, it's just a case of substituting in between the two vacuum states. So let's go ahead and calculate it then. Going to have x minus y is, well, we're going to have a bunch of integrals. Let me pull them all outside of the zero states. And I'm going to label P and Q. So P is going to be associated with the X states. Q is going to be associated with the Y states. And we have the bits, the operator pieces, so the A pieces, which we can't just pull outside of the bras and kets. So we're going to have AP let me actually move this down to the line below times this, and then we can fit everything on one line. So as I said, P is associated with X, so we get the P dot X terms, and we're using Q for the Y term, so it's minus IQ dot Y. As follows. Okay. So in order to proceed then, we need to evaluate the terms inside standards between these vacuum operators. So when you look carefully at this and you try and pull out the only non-zero piece, well, we know by definition that if we have an annihilation operator acting on the vacuum state, we're going to get zero. Okay, so when I do say the product of these two terms, I have two annihilation operators. So when I operate on the vacuum, they're gone. So the only non-zero one I'm going to end up with is going to be a state that has a creation operator on the right-hand side. Okay, so there's sort of four possibilities. So there's this one, which we said is zero. There's this one, which is going to be non-zero because we have the creation operator on the right-hand side. And then we'll have this one, which will be zero. The annihilation operator is going to hit the zero and give me zero. And then I'm going to have this one, a Dagger term, which is also going to give me zero. Because, so when I act once with a Dagger, I'll go from the state 0 to 1. When I act again with a Dagger, I'll go from 1 to 2. And then when I hit the state 2 with a bra 0, those are orthogonal states, so I'll end up with 0. In other words, the only non-zero term I'll get is the product of these two factors. Okay. So the only non-zero piece is going to be 0, the AP, AQ Dagger have these exponential factors. Okay, so in fact, we can pull these exponential factors outside of the 0, 0, like this, and tidy it up a little bit. And so in fact, the only bits we want to then worry about is the calculation of this term. So let's figure out what that is, and we can of course do it using the rules or the tricks that we've been using in previous lectures. So we use the commutation relation between A and A Dagger. You know, this has to give 2 pi cubed delta 3 d minus q. We're just going to use that in our expression. So I'll get a 2 pi cubed d minus q factor plus a q Dagger AP. Okay. Just bringing this term across to the other side. Okay, and then we argue, as we've done before, AP on 0 returns 0. So this term vanishes, and we're left with simply the delta function sandwiched between 0, 0, and 0, 0 is simply going to give us a factor of 1. So we get e to the minus ip dot x, e to the iq dot y, so we have 0, 0, and as I said, these are states which are orthonormal. So this is going to simply be the number 1. So let me just delete it because it's just the number 1. Okay, so if we go back to our expression for the propagator, the x minus y, okay, so it was this stuff that we've now simplified down to this piece times all of this integration stuff, okay? Let me write it down. So we've got the d3p, got the 2 pi cubed, d3 cubed, 2 pi cubed. Okay, so that's all of the integration stuff we had above. And then we just need to put in the result that we've just found for this combination. So in other words, this result. So we've got the delta function. And we have these combination of exponential terms. Okay. So here we can simplify this because we can integrate the delta function with one of the variables. Let's integrate over q. When we integrate over q, we'll lose the 2 pi cubed factors and we'll set p equal to q in our expression. So we'll end up with dp over 2 pi cubed. We'll end up with a 1 over 2 omega p factor, is when we set p equal to q. And since omega q is q squared plus m squared, this goes to p squared plus m squared, which is exactly omega p, all squared, okay? Same thing we've done many times in other expressions. And we end up with this exponential. So we have a minus, let's write it as minus I p dot x minus y. Okay, because we've set, well, we've set the 3 vector piece to be p from the delta function, and then as I just argued, the omega piece also goes to 0, or also goes to, the omega q piece also goes to omega p. So our full 4 vector for q, same as the full 4 vector for 3, or for p, which means we can write it in this way. So this is our final result then for what the amplitude for this propagation starting from a point y, space-time point y, and going to x. Okay, so here's an integral version of the expression. Okay, so we found a basic formula for this amplitude to go from y to x. So next, I want to introduce another propagator, which is the so-called Feynman Propagator. A slightly more complicated beast. Okay, so in theories with interactions, which are types of theories we want to go on and consider, this Feynman propagator is going to show up a lot. This thing is obviously named after Richard Feynman. Okay, so this is going to be particularly important. Okay, so we're going to spend much of the rest of the lecture discussing this Feynman propagator. Okay, so let me just define it for you. The Feynman propagator is written often with the symbol df, f for Feynman. It's minus y as before, and it's defined in the following way. Okay, so we define it as dx minus y, which remember I said you can think of as this is the amplitude that we start at y and we go to x. So we can define it in this way if x0, so if the time component of x is greater than the time component of y, or it's defined as y minus x. Okay, so this is same as saying we start at x and we go to y if y naught is greater than x naught. Okay, Okay, so let's just draw what this means. We're crystal clear. So if we think about position and time on one axis, okay, so if x naught is greater than y naught, this means that y naught occurs earlier. So I've got a position y and a position x. It means I start at the position y, and then I'm going to propagate to the position x. That's if x naught is greater than y naught. Let's think about what happens in the inverse. So when y naught is greater than x naught, and we have the position, we have time. Okay, so now we have x naught occurring before y naught. We can keep our positions the same. So in this case, we start at the point x, and we're going to propagate to the point y. Okay, so this is our definition of the Feynman propagator. There's another way we can express this. We can express it using Heaviside functions. We could express it as theta x naught minus y naught let me use the what we mean by d of x minus y plus theta y naught minus x naught 0. This time we swap the orders. This would be y minus x. Okay, so this theta thing, theta object is the Heaviside function. Well, okay, so what does this do? Well, let's draw theta x minus a. This function has the property that if x is less than a, it's 0. And when x is greater than or equal to a, it's 1. So this is just another way of writing the expression above. That's another way you could write it. Okay, so we can write it using this sort of with the conditions. We can write it with the Heaviside functions. Or we can do it another way using notation that was introduced by Freeman Dyson. That makes use of a new symbol. Let's define a new symbol, call it t. So this is the so-called time ordering symbol. Okay, and by definition, the time ordering symbol acts in the following way. So we have the time ordering on this product of x and y. So these are my operators. What does this mean? This is exactly what we had before, where if x naught is greater than y naught, we get the combination xy. And if y naught is greater than x naught, we get the product yx. Okay, so in other words, this combination d phi x phi y on 0 is d of x minus y. Not it's greater than y naught, it's d of y minus x if y naught is greater than x naught, which is of course precisely what we called the Feynman propagator. Okay. So this is again another way of writing the Feynman propagator. So this is the way that we're going to use most of the times, using this nice time ordering symbol introduced by Dyson. Okay, so next we want to discuss two important properties that this Feynman propagator satisfies. Okay, so the first property that we want to discuss, and I want to show you, is that we can rewrite Feynman propagator in another way. So we can use this time ordering symbol, but we can also write it in this very nice way, which is d4p over 2 pi q, 2 pi to the 4 with I over p squared minus m squared term, and then we have e to the minus I e dot x minus y. Okay, so a couple of things that we have to discuss in here. So first thing we see is the first integral is over the full d4p. Okay, so our previous integrals were all over d3p when we looked at the propagator. This has the d4p. And you notice that we have this factor p squared minus m squared. So the p squared that enters here is the 4 vector. Okay, so p is the scalar that you can construct from the 4 vector rather. Okay, so it's p mu, p mu. And normally p squared, well, for an on-shell particle, p squared equals m squared. So you might think that we have a problem here. But we don't, because what we assume in this form above is that we now treat the 4 momentum components independently. Here, in other words, we don't assume that the 0 component, that's right, it is the 0 component squared. We don't assume that this is EP squared, or sometimes you write it as omega p squared, which is p squared plus m squared. Do not assume that. So we allow p squared, p naught squared to not equal p squared plus m squared. Okay, so this is going to be important because this will allow us to describe off-shell particles. So off-shell particles are by definition particles that do not satisfy p naught squared is p squared plus m squared. Okay. For real physical particles, we do know that the energy and the momentum should be linked in this way, but for off-shell particles, they do not have to be. Okay, so what we want to then show is that this form is equivalent to the form that we considered previously. Let me not go through the full calculation, simply because it's rather lengthy and we don't have a huge amount of time, but let me sketch it, give you most of the details so that you can see how it works. Okay, so we want to show that this form above is the same as our earlier form. So we know from our earlier form that we needed to think about the time ordering of events. So let's think about what happens if x naught is greater than y naught. Okay, so what we want to show, or at least sketch it, is that if we do, okay, so obviously here we have a d4p and we want to get to the result where we have a d3p only. So we need to integrate over the dp naught component so that we end up, so that we go from a d4p to a result that only has dp3 in it. So what we want to show is this dp naught over 2 pi times this I over p squared minus m squared factor. Let's put in the 0th component of my exponential, the p naught component here. We want to show that this would give 1 over 2 omega p e to the minus I, and then we would actually set p naught equal to omega p, which is what we had in our earlier results. So omega p here is the same as EP, and omega p does equal p squared plus m squared. Okay, So if we can show that this holds, then we would find that this form for the Feynman propagator would return to the form that we saw earlier when x0 is greater than y0. Or it's if x0 is greater than y0, we would then have the dfx minus y going to be the same as the result we had earlier. I'll write down just so we remember. So it was d3p over 2 pi cubed 1 over omega p e to the minus I, and here we had p dot x minus y, but where the 0th component of p is now equal to omega p. Okay, so we're going to sketch it as I said, and I'm going to sketch it partly because it's lengthy and partly because it uses complex analysis, so we need to use the residue theorem. And I know that not all universities teach residue theorem and complex analysis as a compulsory part of their course, so I'm kind of aware some of you may not be familiar with the mathematics, and I don't really want to have to spend lectures teaching you complex analysis, okay? But let me sketch it so those who do know be able to extend it easily. So what happens? Well, we have this pole that we have to worry about, the p squared minus m squared piece in our expression. What is this? This is p naught squared minus 3 vector bit plus m squared. Or let's write it as p naught squared minus omega p squared. Okay, so now we're using that omega p squared, rather we're defining omega p squared, be p squared plus m squared. So we see that there are going to be poles in this expression when p naught is equal to plus or minus omega p. Okay, so let's have a look at this. Let's draw it on the complex plane. So using the results of complex analysis. So we put this in the complex plane. We're going to have a pole at plus omega p and minus omega p. Okay. So you can use the techniques of complex analysis to do this integral. So when you use, those of you who know complex analysis, you have to define the contour. So you do a contour integral that then you can relate using the residue theorem, and you usually end up with nice simple expressions. But the point is you need to define the contour. So the contour that we're going to define that gives us the result that we want, namely that this d4p integral comes back to the dp3 integral we had before, is the following pole. So we go around this minus pole in this direction. Our contour does this. And then we close it in the lower half plane. So we have a loop that goes to infinity, essentially. We have this. So we close it in this way when x0 is greater than y0. And with this contour, you can see that we've only enclosed one of the poles. So we've picked out the positive omega p pole only. So you could make different choices. So you could choose a choice where you go this way and that way. So with this contour, you would enclose the pole at negative p. That's fine. And you could do the integral and you could get a result. The point is that if you chose the opposite contour, you would not recover the Feynman. You would not recover the result that we had before for the Feynman propagator. It's only when we choose the contour in this way, so where we enclose the pole at positive p, that we recover the result that we had before. Okay, so then if you go and actually do this integral, so the integral is going to be over this contour, dp naught over 2 pi I we have this exponential factor. Okay, so you can break this into a contour that goes from minus infinity to infinity, and to a contour that goes this great circle, and in principle you can put the contours around the poles and so on. Using, as I said, things like Jordan's lemma to argue that certain bits of this contour will vanish, you can show that this integral is going to be equivalent to the integral only over the real axis, so only going from minus infinity to plus infinity, so the integral we want to do. And then you can use the residue theorem. So residue theorem states this integral is 2 pi I times the sum of the residues. So our residue is at well, we want P naught to go to the pole that we're interested in, that's enclosed inside of our contour, so it's positive omega P1. And then we have this 1 over, oh, well, we need to by this factor and then put in the integrand that we have. Okay, so we're just using the standard residue theorem results. So this factor cancels. Oh yeah, one other thing we should say. So we need a -1 factor here because of the contour choice that we have made. So this is an example of a negatively orientated closed curve. It's negatively orientated because the region that we're enclosing is on the right of the curve the whole time, always on the right of the curve. While a positively orientated contour would have everything on the right of the curve. So if we closed it in the upper plane, it would be a positively orientated curve. So because it's a negatively orientated curve, we pick up this -1 factor when we use the residue theorem. Okay. And what else did we have? Oh, we also had this factor of I that okay, good. So it's I over 2 pi, this factor, times my exponential, times these factors, and then I have this bit plus the -1 that comes from the direction of my contours. Anyway, this will all simplify nicely. So we have, well, we have I times I, which gives -1, and then we have another -1. -1 times 1 is 1. So we end up with a factor 1 from I, and -1, and we end up with a factor 1 from the 2 pi divided by 2 pi. So we end up with simply -I omega p x naught minus y naught have a 2 omega p factor. Okay, so this is how you can recover, so here it was. This is how you can recover the result that we wanted to show. Okay, so if x naught is equal to y naught, and if we choose our contour in this specific way, we have the result that we wanted. Okay. Now, if y naught is greater than x naught, so if we consider the other case, what we would want to do for the other case, have these two poles, we would choose a different contour to calculate it. So the contour we would choose is the contour, I believe it's this one, of the same roots, but now we close the curve in the upper half plane. If we do this case, we would recover the result that we require if y naught is greater than x naught. Okay. So one thing that's can be a little bit frustrating is how to remember this prescription for these contours. I think I've done that the wrong way, actually. Let's double check. I think it should actually be, based on what I'm going to say next, I think it must be, in fact, this one. Let me just double check that. I'll be right back. Hold on. Okay, so indeed, I'm back. This is the correct way. Good. But as I said, it's a bit kind of annoying having to remember which direction these contours go in. So there's a prescription that physicists have introduced that basically automatically tells you which poles you should include in your contours. Contours should be closed, so this is not a very good diagram. But anyway, so what we can do is that we can ensure we get the correct contours with the so-called I epsilon, bad epsilon, let me fix it, the I epsilon prescription. Okay, so the point of this I epsilon prescription is that it automatically gives us the correct poles. Okay, so we're going to use, instead of I over p squared minus m squared, we use I over p squared minus m squared plus I epsilon. This is the I epsilon piece. Okay, so let's see why this works. If we do that, we find that we have poles when p squared minus p squared plus m squared plus I epsilon is equal to 0. In other words, we have poles at p naught at, well, introducing the omega p squared piece again. For p squared plus m squared, it'll be omega p squared minus I epsilon. So epsilon is a small number. We're going to take it the limit that it goes to 0. So this is the same as plus or minus omega p 1 minus I. Let's call it epsilon prime. So we can Taylor expand, or do the series expansion of the series once we factor out the omega p factor, and we'll get a 1 minus I times another small number. So let me call it omega prime. So in other words, we have poles. Let's just draw where they are. We have one pole at p naught is omega p minus I epsilon. Okay, so that would, let's put that here. So it's a positive real piece, the negative imaginary piece, and we have another pole at p naught is minus omega p plus I epsilon. So that's going to be here. So now whenever we draw our contour, so we go along the axis as before, so we don't have to do our funny little tiny contours around the poles. We just move them slightly off the plane. But if I complete the contour in the lower half plane, I automatically include the pole that I wanted, so the one at omega p minus, so the pole up here. And if I enclose the contour in the other way, in the upper plane, okay, in this case, I would enclose, again, the pole that we wanted. Okay, so this gives us exactly what we had before. When I enclose, or when I take the contour in the lower half plane, I end up with a pole at positive omega p. And when I take the contour in the upper half plane, I only enclose the plane at negative omega. This prescription does that automatically. This is why you often see the notation that df Feynman propagator, df x minus y, is the limit as epsilon tends to 0 of p4p 2 pi 4 I over p squared minus m squared plus I epsilon e to the minus I p dot x minus y. This is the form that you will see stated most often, which has this I epsilon factor to remind people which of the roots should be included in our contours. Okay, so that's that's the first property of the Feynman propagator I wanted to discuss. So here's the form that it's most often written as. It's particularly important whenever we look at the Feynman propagator in momentum space. We'll see you get this factor I of p squared minus m squared plus I epsilon. So I said we wanted to consider two properties of the Feynman propagator. So we have looked at one, which is this way to express the Feynman propagator with a four-dimensional integral. So let's look at the second property. And the second property is that the Feynman propagator, the fx minus y, is a Green's function of the Klein-Gordon operator. This is relatively straightforward to show. Okay, so we can just act the Klein-Gordon operator. So this is what I mean by the Klein-Gordon operator, just d mu plus m squared. Let me act on Feynman propagator. Okay, so let's use the form for the Feynman propagator that we've just derived. E squared minus m squared. So I could put the plus I epsilon and take the limit epsilon goes to 0. Or I could remember the prescription, the poles. I guess, since we've just worked it out, let's put it in. So plus the I epsilon, and we want to take the limit that epsilon goes to 0 in the end. And this differential piece is going to hit when it acts on the space-time points. So it's only going to differentiate x minus y. In particular, and this is going to be differentiating the terms that depend on x. Okay, so what happens? Well, happens that the derivative simply pulls down a factor of I, or rather minus I, e mu from the exponential. So I'll get a factor of minus I, e mu, I mu. So with one index up, one index down. Still have the exponential function. Big square bracket. And then let's make sure I've closed these brackets. Yeah, that's correct. And we can simplify this a little bit because we're going to see that we're going to end up with a factor of I. We'll end up with a factor of minus p squared plus m squared. End up with the exponential. End up with p squared minus m squared. So now we can take the limit as epsilon goes to 0. We'll get a factor of minus I, and the p squared minus m squared pieces will cancel. So I pull out the minus sign. So those cancel, and we're simply left with the exponential. Then this is just an integral representation, or at least if I pull out the factor of minus I, this is an integral representation of the four-dimensional delta function. Yeah. Delta 4 x y. Okay, so this is what we mean by a Green's function. So by definition, a Green's function is something that when I act with the operator on something which is a Green's function, I get a delta function back. So this is the definition. Satisfies the defining property of a Green's function up to this factor of minus I. So this minus I, sometimes you see Green's functions defined to be the operator on the Green's function, simply give you the delta function. Here we just have this minus I factor, but doesn't change the story. So why am I showing you this? Well, I'm showing you this because, again, quite often you'll hear people talking about or using the terms propagators and Green's functions interchangeably. Okay, and that's because the propagators that we are considering are also Green's functions. Depending on the big book you'll look at, or depending on the person you'll talk to, you may, as I say, hear people using both terms, calling it a Green's function or calling it a propagator. Okay, so that then brings us to the summary for this lecture. So we started by arguing that we want to move beyond free theories because we want to describe theories that we actually observe in nature where particle numbers can change. So for instance, the Higgs can actually decay into other particles. So in order to fully describe theories with interactions, there's a whole bunch of extra formalism, extra concepts that we need to introduce. So we started to do some of that today by introducing this important term, which is the propagator. The propagator is simply the amplitude for me to start at a state described by a space-time point y and to be found later on at a space-time point x. Okay? So quite often it's given the symbol d. So we write this particular amplitude as d of x minus y. And we can express it in terms of our field operators sandwiched between the vacuum state. And from this definition, we were able to show, or we were able to calculate a result for the propagator in terms of an integral over the 3 momentum. Okay, that's the general propagator. What we're going to find is there's a particular propagator which is going to appear, which is going to be important. This has a special name. It's called the Feynman Propagator. So the Feynman Propagator, well, first of all, it's given the symbol d sub f, and we can define it using this new symbol t, which is the time ordering symbol. So this is a symbol that simply means what we've written in the line below. So if x naught, so if the time component of x is greater than the time component of y, we have this particular ordering for the propagator using the expression above. And if y naught is greater than x naught, we end up with the form where these operators are swapped. Okay. So in practice, the form that we use for the Feynman propagator is this integral over the 4-dimensional momentum space. So now we integrate over d4p instead of d3p. And we have this additional factor, we have this factor of I over p squared minus m squared. And we introduce this IE prescription. So we add in this plus IE, sorry, plus I epsilon rather. We have this I epsilon prescription, which tells us about which poles to include whenever you do the contour integral. So in general, in this expression, we have that p naught is not yet forced to satisfy the relation that p naught squared is p squared plus m squared. So this is a useful thing, as I said in the lecture, because it allows us to describe off-shell particles as well as on-shell particles. And then the final thing that we showed is simply that propagators are Green's functions of the Klein-Gordon operator. So this is why sometimes you'll hear people talking about using the term Green's functions whenever they're talking about the propagators. So for our scalar theory, these propagators are Green's functions of the Klein-Gordon operator. If we had a propagator describing fermions, it would be a Green function of the Dirac operator, and so on.